Recently, the James Webb Space Telescope has spotted something no one expected to see. It might be a new kind of star that was born in the early universe. And the most shocking thing about this star is that it's likely to be powered by dark matter. The thing is, around 84% of matter in the universe doesn't emit or absorb light. Astronomers call this stuff, which can neither be seen directly nor detected by indirect means, dark matter. It supposedly affects visible matter, radiation, and the very structure of the universe. These days, we have several detectors looking for weakly interacting massive particles. That's what dark matter might be composed of. But so far, researchers have found nothing of the kind. One of the most recent studies claims that dark matter might produce long, fine-grained streams radiating out from Earth like hairs and streaming throughout the universe. But it hasn't been proven yet. Now, returning to dark stars that might be powered by this mysterious dark matter. The very concept of such stars still remains hypothetical. Astronomers aren't sure that the images received by James Webb show exactly them. But even if one of the three candidates spotted by scientists turns out to be this new kind of star, it could offer us a glimpse of how stars formed in the early universe. Plus, we would probably be able to find out something new about dark matter and even explain how supermassive black holes appeared out there. The first time someone mentioned the term dark star was in 2007. These space objects could have been some of the first types of stars to form in the universe. They haven't been observed yet, but astronomers think they might be powered by heat that is generated during dark matter interactions rather than by nuclear fusion reactions, like it happens with our sun. Experts believe dark stars would probably look extremely weird. They could have appeared from clouds of hydrogen and helium that drew in excess dark matter. We still don't know the nature of dark matter. But there's a theory that particles of dark matter might be able to interact with themselves, annihilating one another during collisions, and, thus, producing huge amounts of light and heat. Then, this heat could have prevented the cloud of hydrogen and helium from condensing. It means these gases wouldn't have been able to create dense, hot cores similar to those the stars existing today have. And if this gas cloud wouldn't have condensed, dark stars could have grown to truly enormous size. In theory, a dark star could be around 10 times as wide as our planet's orbit around the sun. Imagine the sheer size of such a space monster. These stars would also be millions of times as massive as our star, and their light could be billions of times brighter. It might be the reason why James Webb managed to spot them. To check for dark stars that might be lurking out there, scientists thoroughly examined the images from a JWST survey of early galaxies. They spotted more than 700 objects that could have appeared in the first 100 million years after the universe appeared. That's exactly the time when dark stars were probably born. Light from objects that appeared so unimaginably long ago is stretched, or, as astronomers call it, redshifted. So, the team examining the images picked 4 objects that had already been confirmed to be extremely redshifted. It meant that the researchers were looking at some of the oldest space objects observed so far. These objects might be tiny galaxies from the times when our universe was just a baby. Unfortunately, since they're so far away, the resolution of James Webb isn't enough to figure out whether they're indeed galaxies or just large super bright stars.
What if dark matter doesn't exist? And what if the universe is way older than we thought? Like 27 billion years old instead of a mere 13.8. It sounds insane, but that's what one scientist is saying. But first off, you know how the universe is mostly made up of stuff we can't see. We do have normal matter like planets, stars, and whatnot. And then there's dark matter and dark energy. They are supposed to make up most of the universe. Well, Rajendra Gupta, a physics professor from the University of Ottawa, is saying, folks, maybe we don't really need dark matter or dark energy to explain the universe. Let's have a look at his theory. So, Gupta has been mixing up 2 big ideas. One is called tired light, and the other is called CCC, which stands for covariant coupling constants. But we'll just call it CCC from now on. Normally we think that things like the speed of light or the charge of an electron are set in stone. But what if these so-called constants actually change over time? That's the CCC part of Gupta's theory. Then there's the tired light thing. When we look at distant galaxies, the light we see is stretched out and redshifted. Most people explain that by saying that the universe is expanding. But Gupta's idea is, what if light just gets tired as it travels long distances and simply loses energy? These two ideas can potentially explain how the universe works, and you don't need dark matter or dark energy to fill in the gaps. But why do people even believe in dark matter altogether? A quick backstory. Back in the 1930s, astronomer Fritz Zwicky noticed that galaxies were moving in weird ways that didn't match up with what we could see. So he thought there must be some invisible stuff out there pulling on everything, what we now call dark matter. And since then, scientists have found more clues confirming this theory, like the fact that galaxies spin way faster than they should if we were just counting visible matter. So most scientists think dark matter is like this invisible glue holding galaxies together, making up about 27% of the universe. Well, Gupta disagrees. He also claims that the universe is actually almost twice as old as we think. According to him, the expansion of the universe isn't driven by dark energy either. It's just that the forces of nature are getting weaker over time. He also focuses a lot on redshift, the way light stretches and gets redder as it travels through space. The scientist believes that when we look at the way galaxies are spread out and compare stuff in the old universe to what we see now, the data actually works without needing dark matter to explain it. If Gupta's theory was correct, it would flip everything we know on its head. It could even explain things like how galaxies formed and what the Big Bang really was. We could even figure out more about that leftover glow from the early universe, the cosmic microwave background radiation. But unfortunately, his idea is kinda outdated. Most scientists are sure there's a lot of evidence for dark matter and dark energy, so Gupta would need to find some really solid proof to convince people. Plus, scientists are working on different theories these days. They're measuring cosmic radiation, examining distant stars, and digging through tons of data to see which theory might be correct. More and more powerful telescopes pop up all the time. So we might actually get some answers pretty soon, and most likely they won't involve tired light.
One of the greatest riddles the universe baffles us with is why there is so much more matter than antimatter. The thing is, according to the laws of physics, you can create and destroy matter and antimatter only in equal amounts. But when we look at stars, galaxies, and other large-scale space objects, we see that all of them are made of matter. Only small traces of antimatter can be detected in the cosmos. So the question is, could an equal volume of antimatter exist somewhere? Maybe at one point it just got separated from regular matter? And if it's so, could black holes be that place that contains all the lost antimatter in the universe? If the total mass of supermassive black holes was approximately the same as the amount of that missing antimatter, it could really be the answer. So let's try to figure it out together. At first sight, it may seem that the universe isn't homogeneous and galaxies clump and group together. But if you look at it on a very large scale, you'll understand that the universe has the same properties everywhere. If there was a galaxy made out of antimatter instead of regular matter, we would spot a great number of matter-antimatter annihilation signatures. But since we don't see them anywhere, not in clusters of galaxies, not in individual ones, and not even in colliding clusters of galaxies, we can conclude that almost 100% of the universe is matter. But this is kind of confusing because, according to the current laws of physics, there are no mechanisms that can create more matter than antimatter. Let's take quarks, elementary particles that are building blocks of all visible matter in the universe. Every time we create a quark, an antiquark also forms. And when a quark is destroyed, an antiquark stops existing too. The only way to create more or less matter is to make equally more or less antimatter. The only seemingly logical explanation can be that in the universe's past, more matter than antimatter was created. In the standard Big Bang picture, when the universe was in its early stages, particle-antiparticle pairs of all known and yet to be discovered particles appeared in tremendous abundance. All because at high temperatures and densities, new particles-antiparticles can be produced spontaneously from pure energy. Then these pairs annihilate, producing pure energy photons again. When the universe cools down, it runs out of energy to create new pairs, and the annihilation process becomes prevailing. But what if, at one point in the early universe, something made antimatter collapse into black holes while leaving regular matter behind? After all, we have discovered quite a few ancient supermassive black holes. But then, there's a theory of direct collapse. According to it, some black holes don't need stars to run out of their space fuel and go supernova. Instead, they simply collapse. This process could create seeds, large and fast enough to grow into the young quasars we see today. According to some theories, quasars contain massive black holes. So we can most likely rule out supermassive black holes. But there are also hypothetical primordial black holes. They're often viewed as candidates for dark matter. These holes, if they exist, can't be too light. Otherwise, they'd have decayed. Neither can they be too heavy. This way, we'd have already spotted them. So, most of the possible mass ranges allowing for primordial black holes to be the missing antimatter are already ruled out or very tightly constrained. But in any case, astronomers have managed to estimate the total mass of all black holes in the universe, and it turns out to be approximately 0.007% of the total energy in the universe. And given that there's around 700 times as much normal matter as there are black holes, we can make a disappointing conclusion. Black holes can't be where antimatter is hiding. Neither can antimatter form black holes. The universe somehow managed to make more matter than antimatter at some point in the past. That's actually why we appeared in the first place. But how exactly it happened still remains one of the biggest mysteries in physics today. Can a planet be bigger than its parent star? Well, if you mean a star like our sun, it's highly unlikely. But what if it was a white dwarf, the remnant of a star similar to ours that went out after shedding its outer layers and leaving behind nothing but the core? This core is what we call a white dwarf. Usually, it's around the size of our home planet. If a star had a planet bigger than Earth before it extinguished, it's possible that such a planet could survive all the chaos. In this case, a planet that is bigger than its star might actually exist. And we've even found planetary systems like this. But there's one problem. A white dwarf isn't a real star like our sun anymore. It doesn't produce energy, just sits out there getting cooler and cooler. So probably such systems don't count. For comparison, the sun is working non-stop. It is fusing hydrogen into helium in its core. It has been doing it for more than 4 billion years and is going to keep doing it for the next 7 or 8 billion years. The sun is 10 times as wide as the largest planet in our solar system, gas giant Jupiter. And sadly, you can't get a planet much larger than that. If you start adding mass to such a world, it will get smaller, not bigger. So it seems you can find a planet larger than the sun. But there are also dim red dwarf stars. They're the smallest out there, barely massive enough to maintain fusion in their cores. The tiniest stars that we know about have been discovered recently. If astronomers' conclusions are correct, then both of them can hardly fuse hydrogen into helium. And it takes about 0.077 times the sun's mass, or 75 masses of Jupiter, to be able to do that. And still, they're real stars, just very tiny, smaller than Jupiter. One of them is only about the size of Saturn, which must mean that stars can have planets bigger than they are, right? Well, theoretically. When it comes to practice, you can hardly find such planetary systems. We've found and observed quite a lot of exoplanets, which are worlds orbiting other stars. It seems that there are indeed loads of trends out there in space, different masses, sizes, brightness, and so on. But the main trend? Red dwarfs don't usually have gas giants orbiting them. If they do have planets, those are typically small, rocky worlds, more like Earth. Those are also called terrestrial planets. For example, a red dwarf called TRAPPIST-1 has 7 Earth-sized planets orbiting it. But gas giants circling around red dwarfs are extremely rare. Hardly 1 in 100 tiny stars can boast such a planet. This number can be even smaller since the research has been done using candidate planets which haven't been confirmed yet. Plus, the smallest stars are also the dimmest. It means they are extremely hard to detect, and it's incredibly hard to figure out whether they have planets orbiting them. and if they do, whether these planets are gas giants or terrestrial worlds. Still, it's possible that a system where the planet is larger than its parent star exists. But the probability is statistically very low. At the same time, red dwarf stars are very numerous. They're actually the most common kind of star in the galaxy, making up around 70% of all stars. And even though really tiny red dwarfs are relatively rare, there still must be millions or probably even billions of them in the galaxy. And if there's even a small fraction of red dwarfs with gas giants orbiting them, it might still mean that a lot of such systems exist in total, and some of them can have planets bigger than their host star.
What would it be like to live on a planet traveling around a star so huge that, in comparison to it, our sun looks like a tiny speck of dust? Well, you could find it out if you manage to visit a planet orbiting WOH G64. It's a red supergiant, an enormous star dwelling in the Large Magellanic Cloud, which is a satellite galaxy located not too far away from our home Milky Way galaxy. Red supergiants in the Large and Small Magellanic Clouds provide an excellent opportunity to observationally test the current stellar evolution theory for massive stars. WOH G64 is likely the largest star we have found so far. It's a real heavyweight emitting an incredibly bright light. To understand the sheer size of this megastar better, let's put it into perspective. Compared to our star, the radius of WOH G64 is around 1,540 times bigger. In other words, it's like comparing a tiny grain of sand to a basketball. If we placed WOH G64 at the center of the solar system, the surface of this star would extend past the orbit of Jupiter, swallowing up Mercury, Venus, Earth, Mars, and Jupiter itself. You see, the average radius of Jupiter's orbit is around 1,000 times the radius of the Sun. As for Saturn, the radius of its orbit is around 2,000 times the radius of the Sun. That's why WOH G64, with its average radius being 1,500 times the radius of the Sun, fits right in between. Oh, and if you spread out the star's dust envelope, it would cover a distance of about 1 light year, or 5.88 trillion miles. The star is not only ginormous, but also immensely bright. In fact, it's one of the most luminous stars we know of. Luminosity is the total amount of energy a star emits per unit of time. And the light coming from WOH G64 is around 282,000 times brighter than the light from our sun. But perhaps one of the most amazing features of WOH G64 is the dust envelope surrounding it. In 2007, astronomers, with the help of the Very Large Telescope, discovered that WOH G64 was surrounded by a torus-shaped cloud. It's so thick that to some extent it obscures the star. The dust envelope is made up of the material the star has expelled, and it contains between 3 to 9 times the mass of the Sun. The star we're talking about was discovered in the 1970s by Bengt Westerlund, Olander, and Hayden. That's where the WOH in the name of the star comes from. It's an abbreviation made up of the first letters of the discoverers' names. By the way, Westerlund also discovered another remarkable red supergiant, Westerlund 126. It was spotted in a massive star cluster called Westerlund 1 in the constellation of Ara. But back to WOH G64. Scientists have noted that this star lies very close to or even beyond the Hayashi limit. It is a theoretical constraint upon the maximum radius of a star for a given mass, a condition where the inward force of gravity is matched by the outward pressure of the gas. By now, the star WOH G64 has reached such an evolved state that it can no longer hold onto its atmosphere because of super low density, high radiation pressure, and relatively opaque products of thermonuclear fusion. That's why its average mass loss is among the highest known to us so far. It's unusually high even for a red supergiant. WOH G64 also shows an unexpected spectrum of nebular emissions. The hot gas is rich in nitrogen and has a radial velocity more positive than that of the star, which is quite an unusual phenomenon. The star might have a potential companion, an O-type main sequence star. If it turns out to be true, then WOH-G64 will be classified as a binary star. At the same time, so far, there have been no confirmations of this theory, partly because the intervening dust clouds make the examination of the star very difficult. In any case, WOH-G64 is absolutely fascinating, not only because of its huge size, but also because of its unbelievable luminosity and mysterious dust envelope. It's a great example of how unexpected and amazing our universe can get. Besides, such outstanding large stars are undoubtedly an important astronomical observation. The results of studies of such objects correct the restrictions on the properties of stars within the framework of modern models. For testing the applicability of models, the exceptions to the rules are most valuable.
Scientists have found an invisible star at the Milky Way center, a star that helped our galaxy be born. 26,000 light-years away, in the galactic center, a massive, invisible object started spreading everywhere, and you don't even know that you're breathing it right now. It all started in the 70s, when an astronomer named Vera Rubin was studying the Andromeda Galaxy. She decided to check whether stars move in a predictable way. Now let's say you're spinning a ball on a string around yourself. The closer the ball is to you, the faster it moves in a tight circle. But if you let the string out longer, the ball moves more slowly in a bigger loop. That's how gravity works. And the same goes for planets. The closer ones, like Mercury, zoom around quickly, completing their orbits in months. The far ones, like Neptune and Saturn, take their time, decades, to make one rotation. The stars themselves should orbit the centers of their galaxies the same way. The closer ones move fast, the farther ones are slower, right? But when Vera measured the speeds, she saw something impossible. They weren't slowing down. The faraway stars were moving just as fast as the ones near the center. By all logic, the galaxies should have torn themselves apart, but they didn't. And that meant something was holding them together, something undetectable, some massive invisible object in the galactic center warping reality without ever revealing itself. So she checked over and over with different galaxies. This wasn't a fluke, it was happening everywhere. Rubin had accidentally uncovered proof that galaxies were drowning in something far heavier than all the stars, planets, and gas in our entire universe combined. It was holding us with ghostly hands. Astronomers called it dark matter because it doesn't glow, doesn't reflect light, doesn't seem to interact with anything at all. It's just there. But all the calculations show us that it exists, and not merely exists, but makes up 85% of all the mass in the universe. We know that it sculpted galaxies. Without it, the world as we know it wouldn't exist. And yet, just like with an invisible star scientists found at the Milky Way center, the only way to detect it was through gravity. So how do you find something that refuses to be found? Recently, scientists discovered there might be an invisible star at the Milky Way center, and this fascinating discovery might finally help us understand what dark matter looks like. They began looking for dark matter's fingerprints, any signs of its presence anywhere. They studied how galaxies moved and smashed particles together in giant machines, hoping to create tiny bits of dark matter in the lab. This didn't really lead to anything. They didn't even know what to look for. Is dark matter even made of particles? There was a theory that suggested that it's made of ghostly particles that barely touch anything, or even weirder ones that might flicker in and out of existence in the blink of an eye. There was a problem, though. If dark matter really worked like that, then the centers of galaxies should be packed tight. Tons of matter would be crammed into a tiny space. But in our universe, galactic cores seem strangely soft, spread out, almost gentle. A new theory emerged, and it was wild. What if the dark matter at the heart of galaxies isn't made of heavy particles at all? What if it's made of something so delicate that it behaves more like a strand of hair? These hairs could be made of something incredibly light, lighter than anything we've ever seen, and billions of times smaller than a neutrino, which is already the lightest known particle. They called this idea fuzzy dark matter, and it might change everything we thought we knew about the universe. A team of astrophysicists wanted to test this idea, so they ran a simulation, creating a simple model of a galaxy with two main ingredients: a whole lot of fuzzy dark matter and a little bit of gas, the same kind of gas that forms the stars we can see. They pressed start and just let the system evolve by itself, watching how the two would interact. At first everything was pure chaos, but then the fuzzy dark matter started to gather. It pulled itself together, forming a massive invisible object near a galactic center. The gas followed, spreading throughout this ghostly mass, mixing with it and glowing faintly. And then it suddenly formed something incredible: dark stars. Not typical stars like our sun, blazing with heat and light. Instead, it's enormous, massive, invisible objects, a hybrid of two different kinds of matter. We've never seen anything like this before. An object that would stretch across thousands of light years, and yet they'd be almost weightless, more like cosmic puffy clouds than anything else. Scientists called them Fermion boson stars. Finally, this dark matter thing is starting to make sense. The core of this strange invisible star would have just the right density, not too dense, not too loose, and it looked exactly like what astronomers actually see in real galaxies. If it's confirmed, then it would finally explain how dark matter behaves and works. And if they're right, then every galaxy in the universe could be tied to one of those vast unseen giants. The Milky Way hidden star might be one of them, shaping our galaxy in ways we never realized. What's wild is that this stuff wouldn't behave like normal matter. It wouldn't form anything solid. Instead, it would be more like a complex, ever-moving web of filaments or hairs. This also means that Earth might be completely surrounded by it. Dark matter still follows the rules of gravity. As it moves past planets and stars, gravity pulls it into focused streams, so it's both hugging and passing through our planet, wobbling consistently. If we could see them, they might look like glowing invisible threads everywhere, and they'd pierce right through the planet, stretching far into space. But this is only the beginning. Now scientists need to refine their models, make them even more detailed, and compare their predictions to real galaxies. But this dark star discovery in the galaxy's center isn't our only clue. Luckily, the universe has given us a way to look for that fingerprint: gravitational lensing. When light from a faraway galaxy travels toward us, it sometimes passes by another massive galaxy on the way, or other massive objects with crazy gravity. Instead of continuing in a straight stream, light actually gets bent around the massive object because of that gravity. And when it finally reaches us, it creates a distorted and magnified version of the original galaxy. Basically, it's like looking through a piece of curved glass. If dark matter is fuzzy, then it should leave a strange pattern on these distorted images. Things should be a bit wavy and unclear. Scientists needed the perfect object to study this, and they found one: a faraway galaxy whose light was bent by gravity, creating a strange stretched-out image. They used super-powerful radio telescopes, connected them all over the world, and turned them into one giant telescope as big as the Earth itself. With this, they could zoom in so much that they could see details of that galaxy as tiny as a grain of sand on the moon. Then they ran a huge experiment. They created their own fake versions of this picture, simulations with various sizes of fuzzy dark matter particles. And at a certain point, they found the perfect match. This helped us calculate the exact mass of dark matter particles before we even detected them. And the clues are leading us right to our own galaxy. It seems like densest parts of these hairs, the roots, might be super close in the cosmic scale, just tens of thousands of miles from Earth. That's close enough for a space probe to reach. Now that scientists have found this invisible star at the Milky Way center, we just need to study it up close, send a mission to one of these roots, and then we might finally crack the greatest space mystery of all.
Imagine a universe made of antimatter. In this alternate reality, the building blocks of matter are made up of particles with opposite charges. creating a strange and wondrous world. What would it look like? Would the laws of physics be inverted? Would time run backwards? Buckle up and let's find out. First off, let's figure out what antimatter is. We know that our universe is composed of matter. Matter is made up of tiny particles called atoms. These atoms are made up of protons, neutrons, and electrons, which together form matter and make up everything around us and what we're all made of. Antimatter, on the other hand, is just like regular matter, but the opposite. Just like how superheroes have opposite powers from their villains, antimatter has opposite properties from regular matter. So, while regular matter has protons with positive charges, antimatter has antiprotons with negative charges. Instead of electrons, we have positrons, and instead of neutrinos, we have antineutrinos. It's like the mirror image of everything we're familiar with. Now, here's an interesting part. When an antimatter particle and a matter particle collide, they annihilate each other and release a huge amount of energy. This is both a benefit and a drawback. On one hand, because of this property, studying antimatter is very difficult and expensive. We have to be very careful to ensure that antiparticles don't come into contact with ordinary atoms and don't annihilate each other. On the other hand, the huge amount of energy they release could revolutionize our lives. Perhaps one day, we'll start using them in propulsion systems for space travel. Imagine how amazing that would be! Scientists suggest that at the beginning of the creation of our universe, immediately after the Big Bang, matter and antimatter were equal. But this raises the question, where did the antimatter go? If they were truly equal, our universe would have been instantly destroyed before it could have been formed. Particles and antiparticles would have annihilated each other. Unfortunately, scientists themselves are not sure. They have a theory that the laws of physics were slightly different in the early universe, leading to an imbalance between matter and antimatter. So, after the Big Bang, particles and antiparticles began to mutually annihilate each other. However, for some reason, antimatter started to disappear. In the end, matter won. This process led to the creation of our universe. In the science world, it's known as baryogenesis. However, there are also scientists who offer more grandiose ideas. For example, a team of Canadian scientists from the Perimeter Institute for Theoretical Physics, led by Neil Turok, have proposed their own theory. They suggest that two universes were born at the moment of the Big Bang, our universe and a parallel one, consisting of antimatter. This is where all the antimatter has gone. According to this theory, at the time of the Big Bang, two universes were born, and then they separated. As the distance between these universes grew, the interaction between particles and antiparticles became weaker and weaker, until matter won in our universe and antimatter in the other. But the most important question is, what would this mysterious universe made up of antimatter look like? You may imagine a universe where everything is flipped. The stars shine with an eerie blue light instead of yellow. Buildings are made of glass that reflects light in the opposite direction, and laws of physics work in the opposite way. After all, antimatter has the opposite charge of normal matter, so isn't that logical? However, it's not that simple. Initially, scientists believed that this universe could be identical to ours in everything, all due to a property that used to be known as CP symmetry. The C stands for charged symmetry and means that each elementary particle has a twin with an opposite charge. The P stands for parity symmetry, meaning the symmetry of space. That is, all three directions in our world have opposite directions in the alternate universe. This basically means something like laws of physics are the same no matter what the location is and what type of particle is being considered. So, if you were to run the laws of physics in reverse, or in a different location, or with different particles, the results should be the same. In simple words, scientists initially assumed that the universe of antimatter would be a mirror image of ours. It would be a pretty boring world where everything would be exactly the same as here. But in the 1950s, scientists were mind-blown by an unexpected discovery. Neither of these symmetries held true. For example, if you take a piece of cobalt-60, it will emit particles that spin in one direction. But if you take the opposite of cobalt-60, the particles it emit will spin in the opposite direction. But they were expected to spin in the same direction. So what's going on here? Basically, it turned out that CP symmetry didn't work for certain weak nuclear reactions. The weak nuclear force is just weird like that, I suppose. This observation puzzled scientists for years, and then they finally figured out how to solve this mystery. They added another letter to CP symmetry, T, which stands for time reversal symmetry. This means that the antimatter universe, time must flow from the future to the past. In this case, the CPT property held true, so it turns out that the antimatter universe would be a mirror image of our universe, but with time flowing in the opposite direction. So there may be a version of you in this antiverse, watching this video on your upside-down computer, already knowing the ending. Isn't that crazy? So, although this universe would look similar to ours, it would also be fundamentally different. In this world, things would unravel instead of coming together. For example, broken objects would come back together to form whole objects. People would age in reverse, like Benjamin Button, and apples would fly up from Newton's head back to the tree. This, of course, is all purely hypothetical. It's very difficult for us to imagine a world where time flows backwards. We can only imagine how surreal this inverted reality would look like. But this is what the data suggests for now. There might be something we don't know yet that would make the antimatter world different. But as far as we know today, it seems this is what a mirror world made of antimatter would look like. Scientists are still studying antimatter and its properties. Understanding these properties is important for a number of reasons. First of all, it gives us a better understanding of the universe and its origins. The imbalance between matter and antimatter in our world is one of the biggest mysteries in physics. Studying antimatter can help us understand why this is the case. Second, it would give us a better understanding of particle physics and subatomic particles. This knowledge can help us unlock the secrets of the universe and make new discoveries in physics. And, of course, let's not forget about all the possible technological advancements. Antimatter has the potential to be used as a source of fuel for future space missions and other technologies. We could use this in propulsion systems to travel from planet to planet. We could also use antimatter in medicine, for example, for cancer treatment. Also in medical imaging, antimatter particles can be used to produce high-resolution images of the inside of the body, giving doctors a better view of what's going on. So, in other words, understanding the properties of antimatter is very important for science. It's a fascinating field of study that has the potential to unlock some of the biggest secrets in the universe. A universe made of antimatter would be a fascinating place. It would be very interesting to visit there and see how everything works. And the true nature of an antimatter universe remains a mystery, waiting to be explored and understood. But let's hope that we'll figure these mysteries out in the future.
Now in space, inky darkness between blinding points of light does a great job. It hides black holes, gaping, hungry, and scary. Their blackness makes it really difficult for astronomers to find detailed information about these space monsters. When a powerful and massive star reaches the end of its life, it can't just fade into nothingness. One of the most likely scenarios, the star will run out of its nuclear fuel. Then, in a blazing flash of light, it'll collapse under its own gravity. If the star was large enough, it'll turn into a black hole. There's a hypothetical type of black hole called primordial. Scientists have never gotten any real proof of their existence. These holes are insanely old and quite tiny, by black hole standards, that is. Astronomers believe they could appear several milliseconds after the Big Bang. At that time, stars and galaxies weren't born yet. It means primordial black holes probably witnessed the entire history of the universe. By now, the smallest primordial black holes have most likely evaporated away, but the bigger ones can still be scattered out there in space. But how did primordial black holes appear in the first place? In the very beginning, space wasn't the same. In some regions, it was hotter, in others, cooler, and some areas were extremely dense. Scientists believe these dense spots could collapse into primordial black holes. The most curious thing, though? These holes might be so small exactly because they popped up right after the Big Bang. The longer it took a black hole to appear, the larger it was. The mass difference between older, smaller, and younger, bigger black holes was incredible. Compare the mass 1,000 times greater than our Sun's and that of a jelly bean. Now you get it. There was a theory that primordial black holes could actually be dark matter. This matter is believed to make up around 80% of the mass of the observable universe. Astronomers can't see this bizarre ingredient directly since it doesn't emit light or any kind of energy. The idea remained unpopular for decades, but recently, scientists have realized there are many more black holes in the universe than they used to think, and it means the theory might actually work. And the vast and still hidden from us population of Big Bang black holes could not only make up but be dark matter. After all, astronomers haven't discovered a single dark matter particle yet, even after decades of searching. Some scientists argue that dark matter can't be tons of multi-sized primordial black holes. They would collide far too often for this to work out. Others object that black holes might exist in twos, and then a third one can always approach the pair and replace one of the initial holes. After all, our universe is swarming with black holes, and there's no lack of them. This process would repeat again and again, meaning there would be almost no merges or collisions. Primordial black holes might stay in clusters the size of the distance between our Sun and the nearest star. Each of these clusters can be home to thousands of black holes, all crammed together. A 30 solar mass monster of a black hole might sit at the center, with more common stellar ones occupying the rest of the space. Such clusters can be everywhere astronomers think dark matter is. But so far, this is still only an exciting theory, and some scientists don't support it yet. More data is needed. Now, black holes sometimes behave like massive galactic volcanoes. From time to time, they flare up, but instead of spewing lava, they produce enormous amounts of energy, and it makes gaping holes in the surrounding material and gas. A short while ago, scientists discovered one of the largest craters in the universe. Radio and X-ray telescopes detected a supermassive black hole that threw a temper tantrum many years ago. It happened in a galaxy cluster about 390 million light-years away from Earth. The crater left behind, which was actually a hole punched in the cluster's hot gas, could fit 15 Milky Way galaxies. Whoa! Recently, astronomers have found out that one of the most massive stars in the neighborhood might just have vanished. The star used to hover in space 75 million light-years away from Earth. It's usually too far away for scientists to clearly see individual stars, unless they're really massive, like the one we're talking about. It was gigantic and shining 2.5 million times brighter than our Sun. For the last time, astronomers saw the star's light in 2011, but when they decided to examine it more closely several years later, they couldn't find it. Such huge stars usually go out in an extremely bright supernova, but nothing here, which puzzled the scientists to no end. There's a theory it collapsed into a black hole, and it happened without triggering a supernova first. It does occur among stars nearing the end of their lives, but very rarely. KB 141b is a planet outside of our solar system. At first glance, it's not that different from Earth. It has liquid oceans that evaporate into clouds, condense, and get back to the surface as rain. But instead of water, this all happens with rock. The surface of the exoplanet is covered with lava seas tens of miles deep. The temperature on K2141b reaches 5,000 degrees during the day. That's hot enough for the magma in the oceans to vaporize into the atmosphere. Then, supersonic winds, which can move at the speed of 1 mile per second, carry this rock vapor to the planet's night side. The vaporized magma cools down, becomes liquid again, and falls as a rocky rain. Well, looks like we're gonna need a bigger bumbershoot. A star in the galaxy GSN 069 might turn into a planet the size of Jupiter in the next trillion years or so, all thanks to the star's regular encounters with a black hole. First, astronomers noticed bizarre X-ray bursts. Those were super bright and went off every 9 hours. After examining this phenomenon, the researchers realized it was a star getting flung in a unique orbit around a black hole, and the flashes they saw were the material being slurped off the star's surface. It happened every time the star darted past its greedy host. Over millions of years, the black hole has already transformed the red giant into a white dwarf, and the process isn't going to stop anytime soon. Astronomers have recently discovered some traces of phosphine in Venus's atmosphere. On Earth, this colorless and flammable gas is often found near microbes. That's why a new theory claims there might be life on Venus. But if there is, it could only appear high in the clouds, because no living organism would be able to survive the planet's extreme environment. Its surface is incredibly dry, with no liquid water, and the pressure 90 times greater than that on Earth's surface. The temperatures there reach almost 900 degrees, hot enough to melt certain metals. So that's a no? Methane, a gas that's usually produced by living things, was found on Mars in 2013. European Space Agency's Mars Express spacecraft detected it in Gale Crater near the Martian equator. This discovery might one day answer the question if there's life on Mars. Asteroid 2019 OK scared scientists by sneaking up on our planet in July of 2019. This rather large rock, up to 400 feet across, appeared seemingly out of nowhere. It traveled uncomfortably close to the Earth, a mere 45,000 miles away. That's less than 1/5 of the distance to the Moon. The Sun's outer layer is way hotter than its surface. The temperatures vary from 10,000 degrees close to the surface and a mind-boggling 1 million degrees in the corona. That's the Sun's outermost layer. The reason for this phenomenon might be nanoflares. Those are regular, powerful bursts of heat from the star. Another theory blames the layer that lies just beneath the Sun's surface. It seems to generate a weak magnetic field. That's why, when the energy from this layer leaves the Sun, it heats the corona through a mesh of magnetic branches and roots. The Moon might still be shrinking. Our planet's natural satellite has become 150 feet skinnier than it used to be several hundred million years ago. If its insides keep cooling, it might explain the quakes shaking the Moon's surface. In 2019, NASA's InSight lander, whose goal was to study the interior of Mars, registered the first Mars quake ever. These quakes were coming fast, about 2 per day. Most of them were tiny. You wouldn't even feel them if they happened on our planet. So far, more than 300 Mars quakes have been detected. Those are the first quakes on any space body other than the Earth and the Moon. Another mysterious phenomenon discovered by the mission was bizarre magnetic pulses. They occurred every midnight around the lander. It's still unclear what those pulses are. Maybe after midnight they're gonna let it all hang out, or something. Pluto's atmosphere rises much higher above the surface of the dwarf planet than, let's say, Earth's. It also has more than 20 layers, all of them freezing cold and extremely condensed. Oh, by the way, our Moon also has some sort of atmosphere. Called an exosphere, it consists of helium, neon, and argon. It's 10 trillion times less dense than Earth's atmosphere. Or, really thin.
You may have time traveled multiple times already. You just don't remember it. A recent study says that all your memories of the trip would be completely erased as soon as you're back in the present. And you can blame it on something called entropy. To explain it, we first need to talk about closed time-like curves, or CTC. This is a closed path where a particle could travel, and it ends up right back at its starting point, at the exact same time it left. In other words, it's like a cosmic time loop. Take this notebook paper. Picture each line as a different timeline with a beginning, a middle, and an end. Now, if you roll that sheet of paper, the lines connect. Suddenly, they form a continuous line with no beginning or end. That's what CTCs are. Closed timelines that don't have a starting point. Past and present blend together in an eternal time loop. Now, a more practical example. You're taking a walk around a park. A woman jogs past you, and a dog starts barking. You keep walking, but then, wait a minute. You realize you're back at the exact spot where you started. The same woman jogs by, and the dog barks again. But here's the thing. It's not just that you've returned to the physical starting point of your walk. In a closed time-like curve, you're retracing not only your steps, but every single second of reality itself. Alright, now think about the big moments in your life. Being born, graduating from college, getting married. If all these events are part of one big time loop, that means time travel is possible. It sounds crazy, but there's a concept behind it called the self-consistency principle. It says that time travelers can't create time paradoxes. I mean, time travel can't just be this wild, chaotic mess like those crazy butterfly effect scenarios. Even if you go back in time, everything in your life still has to fit together in a way that makes sense and lines up with what we already know today. I'll explain. Let's say you go back in time and stop your mom from meeting your dad. But here's the problem. If they never meet, then you wouldn't exist. And if you don't exist, how could you have gotten into the time machine in the first place? That's a time paradox. That's why time travel could only work within these closed time-like curves. No matter what you do, the past, present, and future are locked in. They're always going to play out the same way, like a loop. Okay, so now you understand what CTCs are and why they're important for time travel to make sense. Now, we can finally talk about entropy and why it's probably the reason we'd lose our memory after a trip to the past. Entropy is a way to talk about disorder, chaos, or randomness in a system. Imagine a super clean, minimalist bedroom where everything is neatly arranged. Everything's in order. That's low entropy. But then, picture a messy teenager moving in. Every day, clothes, books, and random stuff gets scattered around the room. It's a mess. That's high entropy. In nature, things usually trend toward more disorder unless you actively work to keep them organized. Like this ice cube. It's made up of water molecules, all neatly lined up in perfect order. Low entropy. But if you take this ice cube out of the freezer, it will melt into water. See how the puddle looks messier now? In this form, the water molecules can be arranged in so many different ways. They're all disordered and random. And that's higher entropy. If we apply this idea to time travel within a CTC, the closed time loop, things get even more interesting. According to specialists, a key feature of this circular journey is that the level of entropy has to be the same at both the beginning and the end of the trip. Here's an example. You're just living your everyday life. Nothing too exciting going on, so the entropy level is low. But then, you get inside a time machine and go back to the past, right before you broke up with your high school sweetheart. By traveling through time, the chance of you changing the past and totally throwing your story into chaos is pretty high. Let's say you don't break up with her, and in this second chance, you decide to propose to her. See how everything could go totally sideways, right? So, when you go back to the past, the entropy is at a super high level. Now, you get to the exact moment when you're about to talk to your past love. At that point, entropy is at its peak. You're about to kneel down, show her the engagement ring, when, well, here comes the self-consistency principle, and it throws a cold bucket of water on this whole romantic idea. Remember, in a closed time-like curve, nothing can significantly change the present reality. All the changes a time traveler makes in the past can't cause any historical paradoxes. So, sorry to say, but you're not going to end up with her anyway. You decide to hop back into the time machine and return to the present. You get back into your routine, your job, and well, your single life. After completing the time loop, your timeline is back in order. Now, the level of entropy is low again, just like it was at the beginning of your journey. It's like you did a reset on the system. And that's the bad side effect of all this. Pressing this reset button would probably erase all your memories of the trip by the time you get back to the present time. Unlike in the movies, a time traveler probably won't recall anything. What? Now, answer in the comments. Even if you can't remember what you did after going back to the past, would you still take the risk? I'm guessing your answer would be, yeah, of course. That would be my answer too. After all, we could bring our phones and still make tons of cool photos on this trip, right? Well, no. This is where the laws of physics crush our hopes, again. The second law of thermodynamics says that in an isolated system, entropy, or disorder, tends to increase over time. But this doesn't apply only to humans, but also to non-living things. It's why you can't unscramble an egg, unmix coffee from milk, or take your phone into a time machine. If a time traveler stores any data on their smartphone during their journey, experts believe it will probably get wiped out as soon as the trip ends. All the videos, photos, poof, gone. That's because machines probably wouldn't work properly when we go back in time. For example, let's say you bring a classic analog watch with you. For all the reasons we've already talked about, when you come back to the present, the clock needs to be exactly where it left off. I mean, the clock hands should be in exactly the same position at the beginning and the end of your journey. But to make that happen, it's likely that the frequency and number of ticks during the trip will be different. That could cause small problems in clocks made for regular time, making them unreliable. Something similar could happen with your phone. Its system probably wouldn't work as it should. All these consequences of time travel were described in a study by a mathematician published in 2024. While his theory doesn't determine whether time travel is actually possible, it does point out the strict conditions that would have to be met. And, well, it seems like having a time machine at home might not be as great as it sounds. In the end, you wouldn't remember a single thing about your amazing trip, and you'd probably just end up exactly where you are.
Now imagine something so powerful that it could rip the atoms of your body apart in a fraction of a second. Ow! This something is soundlessly dashing through space, not extinct, not alive, stuck in between. If this terrifying monster were moving towards Earth, we'd be doomed. So, is it? Astronomers have found a fast and powerful space object zooming through our home Milky Way galaxy at over 110,000 miles per hour. That's faster than any rocket we've ever made. This bizarre space object got its name of a zombie star, all because it's the leftover part of a star that passed away a long time ago, but is still moving. This zombie star is a kind of an object called a magnetar, a super small, super heavy ball about the size of a city but heavier than the Sun. That makes it one of the densest objects in space. Only black holes are denser. Hey, let's not forget about me, huh? Magnetars also have an incredibly strong magnetic field. The one our zombie guy has is 100 trillion times stronger than Earth's. That's so strong that if the magnetar came close to Earth, it could wipe out every credit card on the planet just from its magnetism, and we couldn't shop anymore. Plus, if a person got too close to a magnetar, like 600 miles or so, it could pull their very atoms apart, and they couldn't shop anymore. Luckily, this magnetar is very far away and not coming near us. When it was first discovered, it was about 15,000 light-years away from Earth. That's a huge distance, so you don't get to worry about your atoms being disconnected yet. Astronomers first spotted the zombie magnetar in 2008. And since only about 30 magnetars are known in our galaxy, it was a lucky and rare find. Scientists use space telescopes like Hubble and Gaia to watch it over time. That's how they discovered it was moving much faster than they thought. Now, astronomers are trying to figure out how this zombie star got such a big kick. At first, they thought that, like most magnetars, this one was born when a giant star exploded in a supernova, and the leftover core became a super-dense neutron star. According to their theory, it could have happened near something called supernova remnant HB9. That would make sense since most magnetars are created this way. But when they tracked its movement, they found that the zombie star was moving too fast and going in the wrong direction to have come from HB9. They traced its path thousands of years into the past and still couldn't find any exploding star or star cluster it could have come from. This means scientists now have one more mystery on their hands. Where did the zombie star come from, and how was it made? One explanation is that it came from a white dwarf, which is the leftover core of a smaller star like our Sun after it runs out of fuel. Now normally, when white dwarfs explode, they're destroyed completely. But in rare situations, instead of blowing apart, a white dwarf might collapse into itself and turn into a neutron star. This neutron star could then become a magnetar. This unusual way of forming a magnetar also gives clues about another mystery: fast radio bursts, or FRBs. These are very quick and powerful flashes of radio energy from deep space. Some FRBs come from galaxies that are so old there shouldn't be any exploding stars left. But if magnetars can be born from collapsing white dwarfs, that might explain how those FRBs are still happening. In any case, learning how magnetars form could help us explain many strange and powerful events we see across the universe. But so far, the investigation is still on, and no answers have been found yet. Zombie stars wandering across the universe isn't the only mystery we haven't solved yet. At one point, you might come across one of them while traveling through the cosmos. It looks like nothing. At a distance of 700 million light-years away from Earth, there's a hole, a blank void that has very few galaxies. This is a roughly spherical region about 330 million light-years across. Our home Milky Way galaxy could fit there thousands of times over. It's the mysterious Bode's void in the constellation of Bodes. Yeah, makes sense. You see, galaxies look like a giant web. Most of them are parts of long structures called filaments. Those wind through the cosmos, and when they meet, they form regions with a high concentration of galaxies. These regions are what we know as galaxy clusters. But between these clusters and threads, there are huge, empty voids that hardly contain any galaxies. Such voids make up almost 80% of the observable universe, and most of them are huge, from 30 to 300 million light-years wide. The Bode's void is one of the most massive ones. It has even earned the title of supervoid. Astronomers think it might be the result of a few smaller voids merging. But what could have caused such giant empty areas to appear in the first place? The reason might lie in the origin of the universe. In its early days, I wasn't around then, all the matter in the universe was packed together quite tightly. Astronomers even thought it was something like a uniform soup. But soon, random quantum fluctuations started disturbing this matter. Some areas became denser, and their gravitational pull became stronger. They began stealing matter from less dense regions. This made such areas even denser, and they kept attracting more and more matter. At the same time, smaller clumps of matter started drifting further away from the center, forming galaxies. If you visited a star cluster called Palomar 5, you'd forget all about voids and supervoids and even zombie stars. Instead, you'd need to concentrate on surviving, since the region is hiding a swarm of over 100 black holes right in the middle. And those black holes aren't just sitting there, they're at work, shaping the cluster nonstop. Palomar 5 is a group of stars located about 80,000 light-years away from us. Normally, clusters like this are dense and tightly packed, with stars all bunched up together. But Palomar 5 is different. It's spread out and has a huge tail of stars, stretching across 30,000 light-years. This beautiful tail is called a tidal stream. It's like the stars are spilling out of the cluster, creating a long river of light. Tidal streams like this are rare and hard to study. Globular clusters like this one are super old. Some are almost as old as the universe itself. But Palomar 5 also stands out because it's the only cluster we know about that still has a tidal stream attached to it. And the black holes inside the cluster might be to blame. They're pulling on the stars in the cluster, messing with their orbits, and slingshotting them right out of the cluster. Or would that be sling shooting? I don't know. Anyway, these stars are what make up the tidal stream. Over time, more and more stars get flung out. Palomar 5 has way more black holes than expected. About 20% of the cluster's mass is made up of black holes, over 100 of them, each about 20 times the mass of our Sun. Of course, Palomar 5 isn't going to last forever. In about 1 billion years, the cluster will completely fall apart. By then, all the stars will have been gone, leaving behind just the black holes. And these black holes will orbit the Milky Way, like a ghostly remnant of a cluster that used to be there. Even though this cluster is creepy enough, there's something even more eerie you can see in space. Thick clouds of gas and dust called nebulae. One of the most unusual ones is probably NGC 2392, located 5,000 light-years away from Earth in the constellation of Gemini. It was discovered more than 200 years ago and became popular because of its unusual appearance. It's basically a disk of material with a ring of comet-shaped objects. The tails of these objects stream away from the star at the center of the nebula. The bizarre orange streaks in the outer part of the cloud stretch light-years away in all directions. The middle resembles a ball of twine, but in reality, it's a bubble of material blown into space by the wind of high-speed material produced by the central star. Wow!